Three, two, one. Hi, students. Welcome back. We're in the home stretch here. Hopefully you've come back and you've gotten yourself a cup of hot steaming adenosine receptor antagonists. That would be caffeine if you want to look that one up on your own. In this last little mini section, second to last little mini section, we're going to talk about GABA and we're going to talk about glutamate. And one way you can think about these two neurotransmitters, and the reason why I've lumped them together, is because they essentially have opposite actions from each other. And so I'm going to explain how they both work. And glutamate is a little bit complicated, but we can get through it together. But essentially, I want you to think about GABA as the brake pedal and glutamate as the gas pedal, and how we target each and what the effect of drugs that target these will have on a person. So as we think about that as the accelerator and the brake, gamma aminobutyric acid, which just about everyone calls GABA, is the primary inhibitory neurotransmitter in the brain. And you find these GABA receptors often on what are called interneurons, which are essentially little neurons that connect larger neurons, and they act almost a little bit like the traffic cop who's parked on the corner. So they slow down transmission by this inhibitory process. And the overall effect is one of sort of decreasing overall activity. And so with GABA, when you have a little bit of GABA response, you get relaxed, you get a little less anxious. If you push a little harder on that same GABA brake pedal, you start getting drowsy. And if you push really hard on it, you stop breathing. So there's a range of effects, and obviously we're going for the ones that don't involve hypoxia. So benzodiazepines work as agonists. They are partial allosteric modulators at these GABA A receptors, and we'll get to that in more detail in just a moment. But it's also important to remember that alcohol also works on GABA receptors, which is why alcohol and benzodiazepines have somewhat similar effects, and also why we use benzodiazepines to prevent the overactivity that occurs when somebody suddenly stops drinking, who's been drinking a lot for a duration of time. So let's take a look at these GABA receptors. So GABA receptors are those kind of channels through the cell membrane, which is what that dark green double line is there. So there's sort of like a funnel, if you will, and you can see that there are those chlorine receptors just sort of waiting on the chloride molecules waiting on the outside, just waiting for their chance to flow through that central pore there, which you can kind of see from the top. So that's a top view. And as you can see, this is made of 5 different subunits. Well, there's 3 different types of subunits, but together they make this ring that has a hole in the center like a donut. And when it opens up, when there are receptor sites, as you can see on the diagram, for different types of compounds. So like benzodiazepines, there's a receptor site. There's a receptor site for alcohol. There are receptor sites for general anesthetics and barbiturates. And so when we activate those, there's an agonist that plugs into those, that central pore opens up, chloride can flow through, and that, because chloride is negatively charged, it's an anion, it has this effect of decreasing the likelihood of the cell firing. So there it goes, flowing right through. Okay, so this is why these drugs have a fairly fast effect. So you give somebody a benzodiazepine and they start feeling it within about an hour or so after it's absorbed and gotten through the blood-brain barrier and into the brain. So as mentioned, these are all alcohol and benzodiazepines are the most common, but also our Z drugs like zolpidem, they're often referred to as Z drugs because they all have the letter Z in them, bind to a site very proximal to the benzodiazepine receptor. So they are often kind of interchangeable with benzodiazepines, but they're used for sleep. And barbiturates that we don't see very much anymore because they're so darn dangerous in overdose also bind to this site because they're typically irreversible, whereas benzodiazepines, there is an antidote drug just in the same way that there is naloxone for opiates. There's flumazenil for benzodiazepine, and also general anesthetics work in this on this receptor as well. So turning our attention to glutamate, which is the gas pedal here, glutamate is the primary excitatory neurotransmitter. And almost every neuron has glutamate receptors. And there are 3 different types of glutamate receptors, which I'm not going to get into great detail here, but I will get into detail when I talk about ketamine down the road. But what these allow for, these are also these ion channels, so those ionotropic channels that allow for positively charged ions, such as sodium and calcium, to flow through, which increases the likelihood of the cell firing. So let's take a look at the glutamatergic system. Now this gets a little more complicated because we now bring in another type of cell that exists in the brain called astrocytes. Now usually when we talk about psychopharmacology, it's the neurons that get all the attention. But remember, there are 3 types of glial cells, astrocytes being one of them, which have, it's turning out to have, they have a lot more of a role in the central nervous system and in neurotransmission than we originally thought. So astrocytes historically have been thought of as sort of the pit crew for the neurons, that they are there to help sort of resupply them and to clear out the trash. So in this particular schematic, on the top part, you have the presynaptic glutamatergic neuron, and then on the bottom there, on the postsynaptic side, you can see those 3 different receptor types, AMPA, NMDA, which is also referred to as the glutamatergic receptor type, and kainate. And then there are these metabotropic glutamate receptors as well on both the presynaptic and postsynaptic side. Now, on the right, that big purple blob is the astrocyte. So there are a lot of astrocytes for every neuron, and their job is, so the glutamate gets released. It's out here in the synaptic cleft. And the job of the astrocyte is to start clearing that out through these excitatory amino acid transporters. So they're not dissimilar from the reuptake pumps that we see in serotonin, but they're located on the astrocyte. So they're pulling that glutamate out of the synapse, and the astrocyte's job is to transform it, repackage it, and give it back to the glutamatergic cell. So we've got this kind of recycling process here. So now, what does this have to do with depression, and what does this have to do with ketamine, which is, ketamine is a glutamate receptor antagonist. And I just want to point your attention to those extrasynaptic NMDA receptors there at the bottom of your screen. You notice they're in kind of a weird place. They're not at the presynaptic terminal. They're a little further downstream. And what we think happens in say things like chronic adversity in childhood is that it actually causes an increase in cortisol. And cortisol is essentially toxic to astrocytes. So if we decrease the population of astrocytes, then the glutamatergic system is going to have difficulty clearing that glutamate out of the synaptic cleft. So we get all this extra glutamate, we get what's called excitatory toxicity. So when you get this, you get more of those extrasynaptic glutamate receptor sprouting out below the neuron there. And it's thought that when we start getting those, that stimulating those with glutamate is actually associated with BDNF, or that brain-derived neurotrophic factor, or that brain fertilizer inhibition and loss of cell growth, and maybe even cell death. And so this is a sort of a depressogenic pathway. So this is all going to become very relevant when we talk later in the module around ketamine and S-ketamine, and this is an area of robust interest in the pharmacology world, as we think that these glutamate receptors and the drugs that target them could very likely, well, we know that ketamine and S-ketamine are rapidly acting antidepressants, and they have some side effects which some people find challenging. So there's a lot of interest in finding drugs that work on this pathway that don't have some of those side effects. But we definitely know that ketamine has a robust antidepressant effect that occurs within hours to a day or two, much faster than the slow-moving SSRIs. So more to come on that later. Thanks. And just in closing, yes, so these are widely distributed neurotransmitters, both GABA and glutamate, and GABA, of course, being the brake pedal, the most common inhibitory neurotransmitter, and glutamate being the most widely distributed excitatory neurotransmitter in the nervous system. Thank you again.